In this video, we will cover the theory, the preparation technique of ferrite, and also how the resonator antenna works using the magnetic theory.
Assalamualaikum and hi. My name Muhammad Farid Firdaus bin Makrisa, metric number SC18069. So today I will tell about the theory magnetic ceramic. The first magnetic material exploited by man as a navigational tool was a ceramic material. The natural material magnetite FeO4, also known as lodestone. It is thus somewhat paradoxal that it was as late as the mid-50s of this century that magnetic ceramics started making significant commercial inroads. Since then, magnetic ceramics have acquired an ever-increasing share of world production and have largely surpassed metallic magnet in tonnage. With the advent of the information communication revolution, their use is expected to become even more essential. The magnetic characteristics of ceramic materials are of increasing importance as the field of solid-state electronics continues to expand. Although the lodestone was known to have useful magnetic properties at the beginning of the 13th century, it was in 1948 that studies of J. L. Snook at the Philips laboratories in Holland led to the discovery of oxide ceramics with strong magnetic properties, high electrical resistivity, and low relaxation losses. Ceramic magnets are often used in high-frequency devices in which the greater resistivity of the ferromagnetic oxides gives them a decisive advantage over metals. They are used as circuit elements for radio, television, and electronic devices has increased as this technology has developed over the last 30 years. The use of ceramic magnets as memory unit with rapid switching time in digital computers has been essential to the explosion of computer technology. Magnetic ceramics are important as special circuit elements in microwave devices which rely on their permanent magnet behavior. Attribute of ceramic magnets is high intrinsic coercive force. Tooling is expensive, least expensive material compared to alnico and rare earth magnets. Limited to simple shape due to manufacturing process. Lower service temperature than alnico rather than rare earth. Finishing requires diamond cutting or grinding wheel. Lower energy product than alnico and rare earth magnet. Most common grade of ceramic magnet are 1, 5, and 8. Grade 8 is the strongest ceramic magnet available. Ceramic magnet can be broadly classified into two parts, which is ferrite magnet, high DC superconductor magnets.
Now, we are going to see the preparation technique. The conventional solid-state method has been employed to synthesize single-phase YIG through modification of YIG stoichiometry formulation with excess of Fe2O3. The starting raw material are Y2O3, yttrium 99.9%, reagent grade Eldridge, and Fe2O3, ferric 99%, reagent grade Eldridge. Excess Fe2O3 were added in 1, 3, 8, 10, and 20 of percentage respectively to the YIG stoichiometry formulation. Each composition was mixed in a 500 ml polyethylene bottle using ethanol and zirconia balls as medium. Mixing was done using adapted in-house head overhead shakers for 24 hours at 100 rpm. The slurries were dry at 80 degrees Celsius for 5 hours prior to the calcination process, carried out at 1100 degrees Celsius for 8 hours. The calcinate powders were then ground and sieved before compacted into a cylindrical pellets under unaxial pressure at 350 MPa to produce pellet with dimension of 16 mm in diameter and approximately 2.5 mm thick. The pellets were then sintered at 1400 degrees Celsius for 6 hours under oxidizing atmosphere. The phase identification can be done with the aid of XRD, and the results can be analyzed using Analytical Expert High Score Plus software. The morphology can be examined by FISEM, which is supra 35 ppz, and the chemical composition can be confirmed by EDX. For elemental distribution of YIG ceramics, mapping characterization can be done through context 70 tabletop SEM.
Next, I will explain on working principle and mechanism of the antennas. Antennas receive an electromagnetic wave and convert it to an electric signal, or receive an electric signal and radiate it as an electromagnetic wave. A dielectric resonator antenna (DRA) is a resonant antenna fabricated from low-loss microwave dielectric material, where the resonant frequency is predominantly a function of size, shape, and material permittivity. How do we convert it to an electromagnetic wave? That is, to use a closed conductor and with the help of the principle of electromagnetic induction, so you will be able to produce a fluctuating magnetic field and electric field around it. However, this fluctuating field around the source is of no use in transmitting signals. The electromagnetic field does not propagate, instead it just fluctuates around the source. In an antenna, the electromagnetic waves need to be separated from the source and they should propagate. 1/4 of the time period, the wavefront ends meet at a single point. After this, the separation and propagation of the wavefront happens. This is very electric field will automatically generate a varying magnetic field perpendicular to it. If you draw electric field intensity variation with the distance, you can see the wave propagation is sinusoidal in nature. The wave of the propagation so produced is exactly double that of the length of dipole. This is exactly what we need in an antenna. Antenna works as transmitter, where the frequency of the transmitted signal will be same as frequency of the applied voltage signal. Besides that, antenna also works as a receiver, where the same antenna again and apply an electric field. At this instant, the electrons will accumulate at one end of the rod. This is the same as an electric dipole. As the applied electric field varies, the positive and negative charge accumulate at the other ends. The varying charge accumulation means a varying electric voltage signal is produced at the center of the antenna. This voltage signal is the output when the antenna works as a receiver. Next, as you can see, YIG has been used as substrate in reconfigurable patch antennas due to the change in permeability of the material with the applied magnetic field. On applying a suitable magnetic field, the linearly polarized single band antenna shows dual band characteristic, and it shows circular polarization at two resonant frequencies. The greater tunability was achieved by the application of the direct current DC magnetic bias along the width of the patch antenna. possibility of using porous ferrite ceramics as substrate instead of bulk materials for antenna miniaturization. The dielectric and magnetic losses of the proposed porous ceramic were found to be strongly depend on the temperature applied during the synthesis of the material. And also, ferrimagnetic YIG compound could be used as antenna substrate to suppress the mutual coupling between radiating element in a multi-antenna system. Thank you.